So in this video lecture, we are talking about the classification of integrals. What do you mean by integrals is nothing but the solution. That means what type of solutions the partial differential equation have. So let us consider a PDE is of the form, or a first order PDE. A first order PDE means a differential equation which contains the first order derivative. That is f of x, y, z. There are three variables where z is a dependent variable on x and y, and p and q are the partial derivatives of z with respect to x and z with respect to y respectively, equal to 0. We call this as equation number 1. So when the some differential equation is there, the solution is important factor to obtain, and in which space it is there, what type of a solution is there, that is interesting to find out. So essentially, a solution of equation 1 in a region D. A region means it is an open connected set as a subset of R square, where R square is a Cartesian product of R and R, is given by Z as a continuously differentiable function of x and y. For x and y, it is in D. So we are looking for, or the solution is always exist in this space. A D is a region, and which is a function, continuously differentiable function defined on this. If one of the parameter, one compute P and Q from it and substitute them into the equation 1, then the equation reduced to an identity in terms of x and y. Some quantity or some equation which is in terms of x and y, it will be there. So there are different types of solution. Different type of solution is also known as integral surfaces, because in general z is equal to f of xy is there, that will represent a surface, some surface is there. So that's why it sometimes is known as integral surfaces. So there are different types of solution. or I can say integral surfaces. For the first order PDE 1. And here in this lecture we are discussing what are the types of integral solutions are there. So as I told you, this z is equal to f of xy represent a surface, interpreted as a surface in three-dimensional space, and it is called an integral surfaces of the partial differential equation. So let us classify. The first one in this, it's known as a complete integral. When I say integral is itself meaning that a complete solution. Integral means a solution. As I told you, a solution means integral surface. So when I say complete integral means it is a complete solution. So a two-parameter family of solution z is equal to f of xy ab, it's called a complete integral of what? So that is what is the equation we have? Z is the equation is f of xyz pq equal to 0. This is my differential equation is this. So any kind of differential equation is there. When we can say that this z is equal to some function in terms of xy and this a and b are the arbitrary constants, is known as a complete integral if in the region, consider whatever the region we are considering, the rank of the matrix that is, I will say it is M, FA, FXA, FYA, FB, FXB, and FYB is 2. If this matrix, what is the function capital F? Capital F is this. If this is the solution and this matrix has a rank 2, then we can say that that solution is a complete solution. So this is the first classification. The second one that we have is the general solution, or I can say general integral. So a two-parameter family of a solution z is equal to capital XY AB is called a general solution. In this, we'll have, if we take b equal to phi of a, so we'll take this b equal to phi of a, that means b is a function of a, we get one parameter family of solution of equation 1, that is f of x y z pq equal to 0, which is a subfamily of two parameter family capital F of x, y, z AB equal to 0. As z is equal to f of x, y, z nahi aave, so that z should not be here. X, y, a and phi of b, not phi of b, phi of a, because we have taken b is a function of a. Okay, so this is actually a general family. If we can find out the value of a in terms of x, y, and value of, and we'll substitute that value of a here, then that is known as a general integral equation. How we'll do that? So the envelope of this equation, let's say this is 3, the equation 3. If it is exist, what is equation 2 is this one. This is equation 2. If it is exist, it is obtained by eliminating between 3 and its partial derivative with respect to a. So we are taking a derivative of this function with respect to a. So what we will get, that is fa, the derivative of this, and this is the b. So what is the situation? This f is a function of a and b, because there are the two parameter, a and b are the two parameter, and b is a function of a. So ultimately there will be two ways you can go to a. The one is directly to find out a, another one is to this. So it is fa. Fa stands for del f by del a plus fb into del b by del a equal to 0. But what is del b by del a? B is equal to, we have taken as phi of a. We have taken b is equal to phi of a. So del, or I should write not del, but it has to be d, because b is actually a function of only one variable. So that is fa plus fb into db by da. And this, therefore, this will give you fa plus fb into phi dash a equal to 0, because we have given b equal to phi of a. We have taken this. If I call this is the equation number 4, in fact, if this equation 4 can be solved for a, then we'll write this a, which is in terms of, or it is a function of xy, and substituting this value of a into the equation number 3 will obtain the integral surface. So substituting for a in equation 3, we obtain an integral surface. As z is equal to f of xy, the value of a is f of a of xy, and phi of a of xy. We call this as equation number 5. And if the function phi, which defines this subfamily arbitrary, is arbitrary, then such solution, it's called a general solution or general integral. So this is the general integral of equation 1. And we obtain a particular value of this function phi is used, we obtain a particular solution of PD, a different choice of phi. That means if you take your phi differently, that will lead to a different particular solutions. So that is another class, it's known as a particular solution. So particular solution means you have to choose a particular value. So if you choose the phi as some particular value here, you will have a particular solutions. So that also we can write here, that when a particular function phi is used, we obtain a particular solution of the PD. Different choice, if you choose a different choice of phi, may be given or give different particular solution. Of the PD. So if you choose a different choice of phi, that means you choose phi is differently, then you will have different particular solution. So that is another definition, is known as a particular integral or particular solutions. A general integral hence involves the arbitrary function, and the lemma is to show is needed for the solution of the given PD. Okay, so why such, the question is why such phi is always possible, or why such a is always possible, which satisfies our differential equation. So for that we have one, this lemma is there. So it says that let z is equal to f of xy and a be a one parameter family of solution of the equation f of xyz pq equal to 0, then prove that the envelope of this one parameter family if it is exist, is the solution of this equation, that is f of x, y, z, q equal to 0. The solution of this. So what does this say? That if z is equal to f of x, y, and a is the one parameter family of the solution of this, then the envelope, that means the a equal to some value, that's, let's say it is phi of, or b equal to phi of some value, will be also a one parameter family in the solution of this partial differential equation. Let us try to prove this statement. So what is given? Note that the envelope is obtained by eliminating a between two equations. First one is z is equal to f of x, y, and a, and the second one is, if you differentiate this with respect to a, that will give you f a x, y, and a. If I call this as whatever the number is come here, I think so it is 6th number and this one is 7th. Okay. Hence the envelope will be given. So what we have to do, we have to eliminate the a from this two equation. This fa represents the derivative of this f with respect to a, where x and y are constant. So hence the envelope will be given by z is equal to g of xy, which can be obtained by putting, if once you got the value of a, you substitute that value into the here in this equation. That means this a you can express as a function of x and y. So that will be f of xy, a of xy, where a of xy is obtained from this equation 7, from the equation 7, from 7 by solving for a in terms of x and y. So whatever the answer you will have, and from that you solve that equation and you will have the value of a in terms of x and y. And this envelope, that is g, z is equal to g of xy, this is a surface which satisfies our partial differential equation. That means the envelope, because it is a solution family, will satisfy the PDE. PDE, that is f of x, y, z, q equal to 0. For gx, what is gx? That is a derivative of this with respect to x. But g is a function, is this x, y, and a. So here there are three parameters is there. So f, I can say g is a function of three parameters, x, y, and a. A is a function of two variables, x and y. This is the situation. So derivative of g with respect to x will have two paths. One is here, another one is here. So it is del f by del x into del x by del x, which will be 1, so I am not writing that. Del f by del a into del a by del x. And this is nothing but the capital Fxy, because Fa is 0 due to the equation number 7. The equation number 7 says that Fa is 0. So that's why this is as in 7. So this is given del f upon del a is 0. So that just gives you fx or fx. And same way gy is del f by del y plus del y by del y, it is 1, so I'm not writing it. Del f by del a into del a by del y equal to fy. Again the same argument can be given here, that is fa is 0. So that means what we can say, this fx and this fx, that is gx and fx are same. Okay, so that means that it will satisfy our differential equation, this. Okay, so thus the envelope will have the same partial derivative as those of member of family. Okay, they have the same partial derivatives, and the partial differential equation at every point being only a relation to satisfies between the derivatives, and therefore this envelope will satisfy the equation number 1, that is f of x y z pq. So that's, we should write that the partial differential equation at every point being only a relation to satisfies between these derivatives. Thus the envelope satisfies the PD f of x y z pq equal to 0. This completes the proof of the lemma. In the lemma, we have to prove that this family, whatever the family, by eliminating a we got, that family will satisfy the differential equation. That we have proved because the derivatives are same. So this is about the general integral. So till now we have learned two integrals. First one is a complete integral and the second one is a general integral. In general integral, there is a particular type that is called the particular integral by putting the particular values of a. Now the third one, that is a third type of classification of integrals, or I can say a solution. It is the singular integral. Singular integral is also known as singular solution. Okay, so as I told you that integral is also meaning of a solution. In addition, to the general integral, we can sometimes obtain yet another solution by finding the envelope of the two parameter family that is capital F of x y AB equal to 0. Sorry, Z is equal to this, not 0. So Z is equal to this. This is obtained eliminating A and B from the equation. So we'll eliminate this A and B from the equation using the three equations as we have did in my previous video lecture that I have prepared for, in which we have did the same kind of thing. That means if you have this type of equation with two parameter family, then we'll solve three equations. The first one is Z, that is f x y a b. The second one will solve this fa equal to 0. And the third one will solve this fb equal to 0. This fa stands for del f upon del x, and fb is a del f upon del y. And it is called, whatever the solution is obtained by eliminating a and b from this equation, and whatever the solution it's obtained, it is called an singular integral, and it is called singular integral of this PDE. So what is this? Called the singular integral. In addition to the general integral, it has to be a first of all general integral. We can sometimes obtain another solution by finding the enveloping family, that is two parameter family, and if you eliminate this a and b from that family using this three equation, that is z is equal to this, fa is equal to 0 and fb is 0, and whatever the solution by eliminating a and b both from this, that is known as singular integral. Okay, so the question is, this is again a lemma. Can this singular integral is the solution for the PDE? So the question is, or I can say, prove that the singular integral, when I say singular integral, it is singular solution, is also a solution. So it will be a solution for given PDE. Singular integral, as I have talked to you about, that by eliminating a and b from the solution, it's also a solution. Let us give the proof for this. So let z is equal to capital F of x y a b be a complete integral. What does it mean of a complete integral? This solution is known as a complete integral if that matrix, which matrix? Fa, Fxa, Fya, Fb, Fxb, Fyb. If this matrix has a rank 2, then this integral is known as a complete integral that we have taught. Okay, so let us assume that this is a complete integral, and we will show that the enveloping or envelope of this two parameter family if it is exist, it is also a solution. That is our objective. That means by eliminating a and b from this, whatever the solution will get, whatever the equation will get, that equation is satisfying the original equation we have. So note that the envelope is obtained by eliminating A and B between, as I told you, between the three equations. The z is equal to f of x, y, a, b, 0 equal to f of fa of x, a, b, and 0 equal to fb x, a, b. So if you solve these three equations and you obtain the value of a and b in terms of x and y. So I'll say this is the equation number 9, 10 and 11. We'll have to solve these three equations, 9, 10 and 11. And hence what we get, the envelope will be given by z is equal to g of xy. If I want to prove that this g of xy is a solution, I have to prove that gx is nothing but the fx and gy is nothing but the fy. If once we prove that its derivative is same, nothing to prove for the solution. It automatically become a solution. So this g of x is actually what? It is the function of f as a xy, and the value of a is actually a function of x, and the value b we have calculated as a function of xy. So this is the solution where a of xy and b of xy are obtained from the above equation, that is the above equation, that is 10 and 11. 10 and 11 by solving for a and b. So we have to solve this equation 10 and 11 for a and b in terms of x and y. The envelope will satisfy the given partial differential equation. Why? Because for what is gx? Now what is the situation we have? This g is a function, that means f is a function, and f is a function of, here there are 4 parameters, x, y, a and b, but a and b are the functions of x and y. So let me write that things here. That means here is the g. I need to calculate gx. This g is function of 4 parameters. Or I can say first g is a function of f, and the f is a 4 parameter family. X, y, a and b. But a and b are the functions of x and y. So this is the situation. If you want to calculate gx, or I can say gx, then it is x at the 3 places, here, here and here. You have to go via this path. First one is del f upon del x into del x by del x, but del x by del x is 1. So that's why it is fx. Plus, if you go via this one, it is 0. If you go in this path, that is del f upon del x into del A upon del X. So I just write that is FA into AX in short. AX stands for AX is del A upon del X. The third path is this, that is del F upon del B, that is FB into BX. But what is FA and FB? As per the equation number 10 and 11 will gives you FA is 0 and FB is 0. So these two terms will become 0. So this will gives me Fx, because FA is 0 and FB is 0 as in 10 and 11. Same way GY. So as per the same calculation, you have GY is Fy plus FA, FAY, FB, BY, and this will gives me Fy due to the same reason as we have mentioned here. And so what we can say, that is the envelope will have the same partial derivative as a member of the family, and for the same reason as, so the reason is, since this fx, its derivatives are same, okay, so the envelope have the same partial derivatives, okay, the partial derivative, or I can say the reason is as the partial differential equation, the PDE, at every point being only one relation, only a relation to satisfy between its derivative. Satisfies between these derivatives. The envelope if it is exist, it is also a solution. And this completes the proof of this lemma, which tells you that when it will be a singular solution, will be a solution always. Singular solution is a solution that we have proved in the above lemma. Now another lemma is there, which talks about the eliminating arbitrary constants from this. So that lemma is says that the singular integral of this f of x, y, z, pq equal to 0 satisfies the following equations. That means whatever the singular integral is there, it always satisfies these three equations, that is f of x, y, z, pq equal to 0, fp x, y, z, pq equal to 0, and fq x, y, z, pq equal to 0. That means a derivative with respect to p and derivative with respect to q are 0 will always satisfy this equation. Okay, let us gives you and proof for this. Since z is equal to f of xy ab is a complete integral of z is equal to, oh sorry, f of xyz pq equal to 0 of the PDE this. The equation, what does it mean of a complete integral? That means we have to eliminate this equation complete integral. That means z is equal to f of xy ab is the complete integral. So we can substitute this value of z into this uh, differential equation, that is f of x y. Instead of z we can write down f of xy ab. In p is nothing but the del f upon del z upon del x, that is del x. So I'll say it is fx xy ab and fy xy ab. So we have just substituted the value of p, q and z, which is hold identically for all a and b can be differentiable or differentiated with respect to a and b, and hence this leads to what will be gives. So what is this function f? Now we have to differentiate this with respect to a and b. The a and b is here, here and here. So the small f is actually a function of three things. First one is this one, and this one. So I'll say it is capital F, fx, and f1. This capital F is a function of AB. Okay. This is also a function of AB. This will also a function of AB. So fx I can say it is P, and fy we have Q because that was the value previously. P is here, Q. We have substituted the value of P and Q here. So that's why it is P and Q. If I want to calculate FA, this FA, small FA, so I need to differentiate this with respect to A. Then I have three parts. One is this, the second one is this, and third one is this one. So what we will have? We will have FZ, because instead of F we have a Z here. That is the Z function. So it is Fz into Fa plus Fp into Fx A plus Fq into Fy A equal to 0. Why it is Fxa? Because Fx is already there, and then you are differentiating with respect to A again. So it is del square F upon del x del A. So del I del x, and same way it is here on this side. If you differentiate with respect to B, then you will have Fz, Fb plus Fp, Fxb plus Fq, Fyb equal to 0. Now on singular integral, we have given this is the singular integral is there. So in the singular integral, how many parameter is equation contains? Nothing. No parameter is there. So in that singular integral, we have the fa and fb is 0. The singular integral fa is 0 and fb is 0. That we have taken in the previous one also. And therefore, this will satisfy this fp, fa is 0, fb is 0. So it will satisfy fp, fxa plus fq, fya equal to 0, and fp, fxb plus fq, fyb equal to 0. Now this is a Cartesian equation or two linear equations in terms of fp and fq. It will always solution. If you don't want a solution, that means on the surface, that is the determinant on this surface, that is fxa, fyb, sorry, fya, fxb, fyb is non-zero. Okay, and hence if this is non-zero, then you will have fp and fq is 0, because see, this is a equation like a1x plus b1y equal to 0, a2x plus b2y equal to 0, where x and y are small fp and small fq. These are the a1, b1, a2, b2. This system has only one solution if the determinant of the coefficient matrix is non-zero. That is, the determinant is here I have written a1, b1, a2, b2, which is non-zero. Okay, then only one solution is possible to this system, that is fp is 0 and fq is 0, and hence, and if we have this, then we have hence fp is 0 and fq is 0. Otherwise, what will happen? The matrix, if this is 0, what will happen if this is 0? Then you have, just recall that matrix which we have written earlier, that is fa, fb, fxa, fyb, fxb, fyb. Then this matrix will not have the rank 2. Why? Because this determinant is non-zero and fa and fb is already 0. And if this is 0, the determinant of this quantity is 0, this 4 are 0, then the rank will not be a 2. It will be less than that. And so it is, we have started with the complete integral. Okay. And we have started with the singular integral. In singular integral, it has to be non-zero. This has the rank 2. Will not have a rank 2, and which contradict. So the contradictory the fact that z is equal to f of x, y, ab is complete integral. So in the complete integral, we already talked that this matrix above which we have written has to be a rank 2. Why we have did this? Because if this is non-zero, this determinant is non-zero. If this determinant is non-zero, it will satisfy fp equal to 0 and fq equal to 0, and that is our objective. We have to prove that fp is 0 and fq is 0, and f is already 0. Okay, so that's complete the proof of this lemma also. The last one kind of integral is left. It is known as a spatial integral. That is a D, spatial integral. Or I can say spatial solution. Okay, so usually the solution which not come under the all above, that means it is, if it is not singular integral, if it is not complete integral, it is not general integral, then it goes under this complete integral, sorry, spatial integral. Okay, so that is the, so it is saying that usually the three classes that we have talked here, that is A, B and C, given above, include all the integrals of the first order Pde. However, there are some solution of certain first order Pde which do not fall under any of the three classes. Classes we have discussed A, B and C. When I say A is complete integral, B is the general integral and C is the singular integral. Okay, so this three class, if it is not fall under this three class, such solution are called spatial solution or spatial integral. So we have talked about the four class. Complete integral, a complete integral in which that matrix Fk, Fxa, Fya, Fb, Fxb, Fyb as a rank 2. If this matrix has rank 2, it is called complete integral. What do you mean by general integral? If it is a one parameter family, that means you can able to convert your equations, that is equal to f of x, y, ab is there, this is the solution. If you convert your value of b in terms of f of a, then it is known as general integral. And what is a singular integral? Where you can able to find out both the value a and b both. Okay, then it is called spatial integral. And the integral which not come under any of these three, then that is called spatial integral. Let us see some examples based on this. Okay, how the solution is there. See, the method of finding the solution is a totally different project and totally different scenario that we are doing in whole of the unit 1 and 2 to find out the solution of this differential equation. But by looking at the solution, we are just concentrating on the solution. What type of solution is there? So here I am just giving you an example in which I will give you directly, this is the solution of that equation. Okay, and I will classify that this equation is this equation, this solution is this one is this, in that manner. So let's say this capital F of x plus y, x minus square root of z equal to 0 is the general solution of the equation p minus q equal to 2 into square root of z. Okay. But why? Because it contains one arbitrary function. So that is general solution. But see, what is this equation? Is this where P is del Z by del X that we know, and Q is del Z by del Y. So if we just substitute Z equal to 0 in this, it is automatically satisfied. So Z is equal to 0 is also a solution, and it cannot be a general solution, and it is a spatial integral. So it is a special kind of solution because it's not contain any arbitrary constant or something like this. So but Z is equal to 0 is also satisfies P minus Q equal to 2 into square root of Z. Therefore, Z is equal to 0 is spatial integral. So it is a special kind of solution is there. What will be the complete integral for this? The complete integral is containing two parameters over there. So the complete integral is actually, now how we can get this, that is a different task. Given this PDE, to find out the integral, it is a different, there are different methods are there that we are going to discuss later on. But the complete integral is this. The complete integral of this PDE is square root of Z, A Z plus B upon A minus 1 plus B, where A and B are the, sorry, A X plus Y is there. Huh? So this A and B are the arbitrary constants. So this is a complete integral for that. If you want to check whether it is a complete integral, you have to find out what is the matrix of that, rank of that matrix. Okay, let us have another example. Let us say this f of x, y, z pq is equal to z minus px q into y minus p square minus q square equal to 0. This is the differential equation is there. Now one should check that the two parameter family that is z is equal to capital F of x y ab is equal to ax plus by plus a square plus b square is the solution of this differential equation. That you can check easily, because if you differentiate this with respect to x, del z by del x is a and del z by del y is b. If you substitute that one here, whole equation you can just substitute here. That means the value of p is a and q is b. Substitute here, where z is ax plus by plus a square plus b square. It will satisfy. It is easily to check that this is the solution of this differential equation. Okay. So it is if I want to say it is a complete solution, I can say right now it is a solution. But if I want to write it is a complete integral, as I need to check what is the rank of this matrix, that is FA, FXA, FYA, FB, FXB, FYB. What is FA? The derivative of this with respect to A, that is x plus 2a. What is fx? Fx is a, and if you differentiate, so capital Fx is a, that is a derivative of this with respect to x, and then you are differentiating with respect to a. So Fx a is 1, so this will give me 1. And what is Fy? Fy is b, differentiation of Fy at b, sorry, Fa is 0. So this will be 0. Fb, you can say it is a b, sorry, y plus 2b. This will be 0 and this is 1, that you can check. And one should note that this is of rank 2 because the determinant of this quantity 1001 is non-zero, or minor of order 2 is non-zero. So that's why it has rank 2. So I can say it is a complete integral as this is of rank 2, is of rank 2. Okay, so this actually all the things is not required for me. And it satisfies the given PD. Okay. So the complete integral is clear. How to check it is a complete integral. Now let us talk about the general integral. So what I'm taking, I will take this. Take b equal to square root of 1 minus a square. Then z is equal to capital F of x, y, a, and the value of b is this 1 minus a square, square root. As per the equation, that is ax plus by plus a square plus b square, we substitute that value. That is ax, the value of b is this, so that is square root of 1 minus a square into y plus a square plus b square, so that is the square of this, that is 1 minus a square. A square will get cancelled out, so we'll have ax plus square root of 1 minus a square into y plus 1. So this is the equation we'll have. Now we need to eliminate a from this and find out what is the value of a and substitute here. That is gives you a particular integral. This is the general integral. This is the general integral because we have substituted the value of b. Now let us calculate Fa, Fxa, del f upon del a. The derivative of this with respect to a. So that is gives me x minus a derivative of square root. Okay, that is 1 upon 2 into square root of 1 minus a square, and the derivative of minus, so it is minus 2a y, and the derivative of 1 is 0. 2 will get cancelled out. And Fa is 0, that we have started with. Now we have to eliminate a from this. So what we get? We'll have x is equal to ay upon square root of 1 minus a square. So that is 1 minus a square x square equal to a square y square. So if we can calculate the value of x square y square from this and substitute here, so what we get? The value of let's say it is x square minus a square x square equal to a square y square. So this is x square equal to a square will get common, x square plus y square. So we'll have a square will be x square upon x square plus y square. So a, we have a here. So the value of a, I can say it is x upon square root of x square plus y square. And 1 minus a square will be 1 minus x square upon x square plus y square. So that will gives me y square upon x square plus y square. Okay, and we'll substitute that value of 1 minus a square and a from into this equation. So now we have z is equal to a x plus square root of 1 minus a square y plus 1 is there. The value of a is this x upon So it is x square upon square root of x square plus y square plus 1 square root of 1 minus a square. The square root of this is y upon square root of x square plus y square, and this y is already there, so it is y square plus 1. And if you can just take the LCM, so it will left with square root of x square plus y square plus 1 z, and hence we'll have z minus 1 square equal to x square plus y square. So this is the elimination of a is there, and this is known as a particular integral. What is this? It is a particular integral or solution of the PDE. This is the particular integral. This one, which we have written here, z equal to, this is the general integral. If you assume here I have taken the value of b is this. If you take another value, you may have some another thing. Let us take another thing. So now let us take b equal to a. If you take b equal to a, we have an equation is ax plus by plus a square plus b square. This is our solution. If I take b equal to a, then it is ax plus ay plus 2a square. This is our solution. We'll calculate what is fa. We need to eliminate a from this, equal to 0, which will gives you x plus y plus 4a equal to 0. So the value of a we can have is this a equal to minus x plus y upon 4. You substitute this value of a here into this equation. I can say this is star. So from star we have z is equal to a, that is minus x plus y upon 4 into x plus minus x plus y upon 4 into y plus 2 into x plus y upon 4 square minus. And we can simplify this, all the things. So what is this? If I can take common out minus sign, x plus y upon 4 is common from this two. We're left with x plus y. Here it will be, what is the things we got? It is plus 2 upon 16 x plus y square. So this is minus 1 upon 4 x plus y whole square plus 1 upon 8 x plus y square. So ultimately minus 1 by 4, 1 by 8 will gives me 1 by 8 minus 1 by 8. So that will gives you z is equal to minus 1 by 8 x plus y whole square. So finally the 8z equal to minus x plus y whole square is this is another particular integral, particular solution of the given PDE. So in the same manner, if you can choose another solution, that means if you choose another value of b here I have taken a b equal to a, here I have taken b equal to square root of 1 minus a square. If you choose different values, then you will have a different solution, and that each solution is known as a particular integral or a particular solution. So that is the way is the particular integral is behaved. The last thing that we need to mention, that was the lemma which we have discussed, that the solution, that is this solution. So here this is the example, and we'll talking about the same example, that the singular integral, what will be the singular integral for that? So a singular integral means to obtain the value of a and b both. That is known as a singular integral. So we have talked about the complete integral for this. We have talked about the general integral for that. Now we need to talk a singular integral for that. So for that, these are the particular integrals. Now we'll talking about the singular integral. So now from the equation, that is z is equal to ax plus by plus x square plus b square, a square plus b square. The condition fa equal to 0 and fb equal to 0 becomes, because we need to eliminate a and b both from this into the singular integral, we have to eliminate a and b both. fa will be x plus 2a. The derivative of this, partial derivative of this with respect to a will gives you 0. And that will gives you the value of a is minus x by 2. And fb equal to 0 will leads to y plus 2b equal to 0. You can just see that the derivative of this with respect to b, that is y here and here it is 2b, and will leads to the b equal to minus y by 2. Now we substitute, putting this value minus x by 2 and y b equal to minus y by 2 in the original equation, that is this equation. Let's say this is double star. In double star, we get z is equal to, it was a into x, so it is minus x square by 2 minus y square by 2 plus x square plus y square. And if you can, so this is, yeah, no, x square by 4 y square by 4, because it is x by 2, so a square plus b square, x square by 4 y square by 4. So this will leads to minus x square plus y square by 4, because minus 1 by 2 plus 1 by 4 will gives me minus 1 by 4, and hence it is 4z is equal to minus of x square plus y square. It is your, this is the singular integral or solution, singular solution, or I can say integral of the given PDE. Okay, so that is for this, regarding this classification of integral is there. Okay, so that's it for today. If you have any questions, you can ask. If you have not understood any topic while I'm discussing, you just ask back if you have any.